Hello, welcome to Chapter 12. Uh, we're going to be learning about the tests on the population mean today. We already learned about test statistic. Now we're going to learn about T-test statistic. That's what happens when we don't know the population standard deviation. Now I think I mentioned this in class, but these were invented by a Guinness brewer because he wanted to find a better beer. So he wanted to try in many experiments with the different ingredients in beer, and he wanted to hone in on what was actually the best tasting beer. So he brought in statistics in order to um, have some way to evaluate that. And during that process, he noticed that it doesn't follow the um, population or the normal population very well. So he came up with these t values. Now, the one sample t statistic, if is it and the t distribution. If we draw an SRS from size n from any population that has a normal distribution with a mean of mu and a standard deviation of sigma, one sample test statistic t is equal to x bar minus mu over s divided by the square root of n. The only thing that's different from this, from our z-test statistic, is now we don't have sigma, we have s. All right, here is the t distribution table. So if you take a look at this, this is it's the same one that we use with confidence intervals. Um, it's just we're going to be concentrating on the top part rather than the lower part. All right, so suppose we have a null hypothesis where the mean is 5 and the alternative hypothesis the mean is greater than 5. Based on a sample size of 20, obtain the t-value of 1.8. Let's find the p-value. All right, so our t-value is 1.8. Since our n is equal to 20, our degree of freedom is 1 minus that, which is 19. So if we look back at the chart, we look for 19, and we look at these numbers above that line. Now, 1.81 was my t-value, and if we come across here, it's going to be between 1.729 and 2.093. So it's right here. So it's somewhere between 0.05 and 0.025. I would guess it's a lot closer to 0.05, maybe 0.04 or something like that, because it's closer to 1.7 than it is 2.09. So we can't, from our tables, tell you the exact p-value, but we can say that our p-value is between 0.05 and 0.025. Now that will help us. It would reject a null at the 0.05 alpha level. It would fail to reject it at anything lower than this. So like at a 0.01 level, it would fail to reject. So it'll help us with those values. However, if our alpha level, for any strange reason, was 0.03 or 0.04, this wouldn't help us. So we have a calculator method where you do TCDF. We'll do the min, max, and now we have to type in our degree of freedom. So you hit second variables on your calculator. On my calculator, it's number 5, TCDF. We'll go from 1.81 to a very large number, which will be our max, representing infinity, and our degree of freedom is 19. So if I do it out, I get 0.043. So that was close to what I guessed. I guess 0.04. 0.043 will be our p-value. Now our one sample t-test, if we draw an SRS from size n, and we're testing our null hypothesis, this is our z statistic that we already talked about. same as with z-scores, if our alternative hypothesis is greater than, we just check the right-hand side. If it's less than, we just check the left-hand side. And if it's not equal to, we have to check both sides. So we have to do 2 times the probability of either of those. All right, diet colas are use artificial sweeteners to avoid sugar. These sweeteners gradually lose their sweetness over time. Manufacturers therefore set up a new cola, a new test. Therefore, test new colas. Sorry, I can't read. For loss of sweetness. So we're checking for a loss of sweetness. That's something to know before marketing them. Trained tasters sip the cola along with drinks of standard sweetness and pour the cola on a scale of 1 to 10. The cola is then stored for a month at a high temperature to imitate the effect of 4-month storage at room temperature. So each taster tests the cola again after storage. Period. I forgot my period. Our data are the differences in the taster scores. So let's do a hypothesis test. So our first thing we need to write is our hypotheses. Our null hypothesis would be that nothing changes. So the mean difference would be 0. Our alternative hypothesis would be that it loses sweetness over time. So this is before minus after. So if I wanted to, so if it had 10 and afterwards it was 8, that would be 2. So if this is before, this is after, that would be 2. So that means that it lost a sweetness of 2. So if our mu is greater than 0, then that would mean that it loses sweetness. Alright, so now we have to define mu. Mu is the mean difference in sweetness of diet colas. Alright, so now we want to check our conditions. Let's see if these have been met. Does the data come from a random sample? That doesn't say anything about a random sample. It doesn't say random sample. So we don't know if it's an SRS or any type of random sample. We just have no idea. All right, now our calculations. Oh no, that's just one condition. Let's check normality. So to check normality, can move that over here. We'll have to graph these and see if this is approximately normal, because this data right now is not enough data pieces for us to use the central limit theorem. So I'll put these in my calculator and see what. All right, I put them in my calculator, and I came up with a box plot that looks something like this. Now, this is slightly skewed to the right, but it's not enough to say that it's not normal. So, so we can say, or slightly skewed to the left, I'm sorry. Data is slightly skewed to the left. But it is approximately normal. With this few data points, it's hard to find something that will be exactly normal. So, Now let's do independence. So there are 10 data pieces. So um, we can say data is independent if there are more than 10 times 10, which is 100 colas that are efficient. And that's for sure for many, many cans of cola. So, so our calculations. Wrong color. Alright, so our calculations, maybe I'll do this in a different color just to separate it. So our t statistic, we take x bar minus our null mean over s over the square root of n. So our x bar, we do one variable stats of L1. I got an x bar of 1.01 minus 0 divided by our s, which is 1.196 over the square root of 10. Well, if I just did the top, I'd get 1.02. 1.196 divided by the square root of 10 will get us to 0.378. So 1.02 divided by that answer will give us a t statistic of 2.697, let's say if we round. Alright, so we have our t statistic. Now let's find our p-value. If I look back at the chart, our degree of freedom is no longer 19. It'll be 10 minus 1, which is 9. Now our t-value that we came up with was 2.69. So 2.69 would be in between here. So between 0.01 and 0.02. So we could write p-value is between 0.01 and 0.02, and that would be all that you need for the calculations. Now if we wanted to be more specific, we could do a TCDF from 2.697 to a very large number with a degree of freedom of 9, and I got p-value of 0.01225, so 0.012. So if you wrote it like this, or if you wrote it like this, both answers would be acceptable. So our interpretation. So first thing, we either reject or fail to reject the null. Now they don't give us an alpha, so we would use 0.05 as our standard. So this is lower than 0.05, so we reject the null hypothesis because the p-value is 0.012. So we rejected that, so we said we have evidence that sweetness is lost in the shipping process. All right. Now we're done with that problem. Now on our t, graph, you can see that this is our t distribution. Remember, this is not a normal distribution, it's a t distribution, so it's a little bit different. It's a little bit wider than a normal distribution. And a t of 2.70 on the right-hand side would be 0.0123. And hopefully that's what we get. We're a little bit more specific. All right. So you can also get these on Minitab results. This is a test of mu is equal to 0.00 versus a mu GT means greater than 0. Now it gives us the readout. N is 10. Our mean is 1.02. Our standard deviation. Our standard deviation measure, where if we can get this by taking 1.196 divided by the square root of 10. And then our t-value is 2.7, and our p-value is 0.012. Now, in some questions on the AP test, instead of having you go through all the calculations, they give you all of this business, and it's your job just to interpret everything. Here's another way to do it. This is how Fathom would do it. This is easier to read. It has a null hypothesis that equals 0, the alternative hypothesis that is greater than 0, and then count, mean, standard deviation, standard error, student t's. Then we have degree of freedom and p-value. All this is self-explanatory, I believe. All right. Now, an investor with a stock worth several $100,000 sued his broker because of a lack of diversification in his portfolio led to poor performance. Here are the monthly rates of returns for 39 months that he has invested with his broker. Are these returns compatible with an S&P average of 9.5%? All right, so we have what we want it to be, and these are our values. So let's see if he is consistent. Take a second and do this on your calculator, and write this up, and then I will, and then I'll show you my answer. So pause it right now and see how you can do. All right, hopefully you're done. Now to go through this, my null hypothesis is that the mean is 0.95, and my alternative is that it's not 0.95. And I forgot to even define my mean. Mean is the average return for a month. From this guy's retirement account. So conditions data does not say that it comes from an SRS, and data is approximately normal by the central limit theorem because n is greater than 30. Now we have to assume that each month is independent. Now in this case it doesn't actually make sense to do the 10, the population is 10 times as big as the sample, and that's because we're not sampling with our replacement. We're just looking at each month. Now the calculations, I have a t test statistic as negative 2.14. So since this is not equal to, we have to multiply 2 times our p-value. And I got 0.388. Now to interpret this, we reject the null because the p-value is 0.0388. We have evidence that the returns are different from the average of the market. So let's find a 95% confidence interval for this investor's portfolio. So if we want to do a 95% confidence interval, we would do x bar plus or minus t star times s over the square root of n. Now this is pretty easy because we have all the information. My x bar is negative 1.1 plus or minus. Uh, T star would be 2.042 times our s, which is 5.99 over the square root of 39. Now if I multiply this all out, this would be 1.96. So this goes from negative 3.06 to 0.86. So notice my 95% confidence interval did not contain my null mean of 0.95. So that's another way that we can say we would reject the null hypothesis, because the null mean is not in this confidence interval. So what's a type 1 error in this situation? So type 1 error is when we reject the null, but the null is actually true. So we have evidence that that returns are different from the national average, or the S&P 500. But they actually are equal. Now, what are the consequences of this? Since this guy got less returns than the average, he would find another investor. But um, he'd find another investor, but his investor was actually doing fine. A type 2 error is when we would fail to reject the null. So if I did a type 2 error in this situation, that would be that I got a value in the white area. So I would fail to reject the null of 0.95, but it really is different than 0.95. So in the type 2 error in this situation would be you get a value that says that it's not much different than 0.95. However, it really is. And a consequence of this is the person who's giving the money might not get the returns that he would hope to get. All right, hopefully that helps you get through the homework. Good luck.